Shri Gurubhyo Namaha. Very good morning, my dear children. In the previous session, we had a brief lecture on standard electrode potential, standard hydrogen potential Xii, how to calculate standard potential for fuse cell, and started with electrochemical series. I am sure, my dear children, you must have understood all the points and prepared your own notes for this particular chapter. Okay. Now, for today's session, let us continue the same topic along with few numericals. Children, I am requesting all of you to note it down the important keywords given in the slide simultaneously, which will be useful for you to solve the numericals. Now, go through the tabular column on the right hand side. The elements, whatever available in the list, are gaining those electrons. So, it is considered to be a reduction reaction. Now, the potential value whatever we are getting will be considered to be standard reduction potential. I hope you remember. Once again, let me repeat. From the list on the right hand side, we can understand the potential values given for reduction reaction. So, it is standard reduction potential, and the element in the top are good oxidizing agent or weak reducing agent, whereas in elements which is available on the bottom are considered to be weaker oxidizing agent or stronger reducing agent. You could see the stronger reducing agent value will be negative, whereas the stronger oxidizing agent value will be positive. Now, this series has been established by measuring the potential of various electrodes along with what? Along with the Xii. Okay, children. It is the list that describes the arrangement of elements in the order of electrode potential value. I am sure you remember standard electrode potential is obtained by measuring the voltage when the half cell is connected to the Xii under standard condition. Okay. Now, elements that displays a greater tendency to lose electron, that is to their solution, are usually categorized as electropositive. Similarly, elements that acquire electrons are said to be electronegative. I hope this is not a difficult point. They are usually below the element hydrogen to the series, children. Please see the values. Now, as you see, below hydrogen we have got lead and zinc or magnesium or lithium, all are placed below hydrogen. Okay. So, we can figure of the order in which metals will replace one another from their salt. It is the basic for displacement reaction. We have studied about it. So, we can understand clearly electropositive metals generally replace hydrogen from acids. Okay. Now, what is the next point? The next important point is metals that exist further apart from each other on the scale will react with a higher value for corrosion than ones that are close to each other. Please remember, close together. We'll discuss some example. If we consider zinc, the value is minus 0.76. You could see in the tabular column zinc which is having a value as minus 0.76, and copper the value is 0.34, minus 0.34. Far apart on the scale. This means, children, you would never have a copper pipe draining water onto a zinc water roof. Please understand. So, this is the first application of it. My dear children, by this you must have understood the series help us to identify good oxidizing or reducing agents. Okay, note it down this. All the elements appearing on the top of the series are the very good oxidizing agents. Once again, let me repeat. They have a positive value of SRP. What is that? Standard reduction potential. Okay, example, fluorine after reduction. Fluorine electrode with the standard reduction potential value of plus 2.87 volt is a strong oxidizing agent. Okay. And lithium on the bottommost one with the value of minus 3.05 volt is a strong reducing agent. I hope you can understand. Okay. Now some more important points to be discussed are, note it down. The greater the reduction potential of an element, the more easily it will be reduced. Okay. Now meanwhile, elements that have low reduction potential will get oxidized much quickly. That is, it will be releasing the electron, not gaining the electron quickly and easily. Elements who give up electron without any difficulty have negative values, or it will be having low reduction potential. Okay. Elements that do not give up electrons easily, for example, fluorine will be gaining electron, whereas lithium will be donating electron. So we know that to compare about. Elements that do not give up electron easily rather than accept electron have positive or higher reduction potential. Okay. I hope you are following me. Stronger reducing agents that have negative standard reduction potential are usually situated below the hydrogen. Stronger reducing agents. Which one is a stronger reducing agent here? Lithium, sodium, magnesium, aluminum, water. Water will be acting as both oxidizing as well as reduction. And iron, cadmium, nickel, all are placed below hydrogen. You could see the values. It starts from minus 3.04 from bottom and ends up around 0.13. Weaker reducing agent with positive SRP are found above the hydrogen. Again, above the hydrogen you could see from fluorine to copper. The value starts from 2.87 to 0.15. Okay, we know that the hydrogen value will be 0. So, as we move down in the group, the reducing agent strength increases while the oxidizing agent strength will be decreasing. Using the values given in the standard electrode potential table column, we'll solve few numerical. The first one is, arrange the following metals in the order of their reactivity. That is, how they displace each other from their salt solution. Align the metals in decreasing order: copper, iron, aluminum, zinc and magnesium. Okay, for this numerical, first we have to remember two things. What is that? Zinc has less reduction potential than copper. The second one is, that means the one with less reduction potential metal will displace higher reduction potential metal. Okay, now using the table we have to note it down the standard reduction potential value. According to that, for copper it is 0.52 volt and iron it is minus 0.44 volt. The third one, for aluminum it is minus 1.66 volt. For zinc minus 0.76 and for magnesium it is minus 2.36. So, according to the reactivity, the given metal replace the other one, the salt solution in the said order. That is, when you arrange the values, we will be getting magnesium, then aluminum, zinc followed by iron and copper. So, this is order using the value. Now, the next numerical is standard electrode potential given us. You could see the values. Magnesium 2 plus converted into Mg, the value is minus 2.37 volt. Heg 2 plus 2 Hg plus 0.79 volts. Cr 3 plus 2 Cr minus 0.74 volt. Ag plus 2 Ag 0.80 volt. K plus 2 K minus 2.393 volt. So, in the order of increasing of reduction power, arrange the given metal accordingly. Two things you have to remember. The first one is, reducing power is the ability to get oxidized. Higher reduction potential implies to get reduced. This means lower reduction potential implies easy to get oxidized. That is, conversion of Cu plus to Cu is more feasible. Now, which is having a least reduction potential will be oxidized first. So, according to this, you could see K plus converted into K will be minus 2.93. The second one is Mg2 plus 2 Mg is having minus 2.37 volt. Third one is 0.74. Which one? For chromium 3 plus 2 Cr will be minus 0.74 volt. Fourth value is Hg2 plus 2 Hg. You note the value. It is 0 plus 0.78 volt. The last one will be Ag plus 2 Ag is plus 0.8 volt. Okay. So this is a order of reducing power. We can arrange the given metals. The next numerical is depict the galvanic cell in which the following reaction takes place. Zinc in solid form reacts with Ag plus in aqueous form to give Zn2 plus in aqueous form plus Ag in solid form. Also find the negatively charged electrode. Current carriers in the cell. Third one, at each electrode the individual reaction. Okay. Now children, I think you can visualize the apparatus construction. Zinc will be anode and zinc sulfate solution is a electrolytic solution in the left hand side of the container, and Ag is connected as a cathode and AgSO4 as electrolytic solution in the right hand side of the container. I think you can imagine this. Now Zn converted into Zn2 plus electron released will be anode side reaction, whereas Ag plus gaining those electron to convert it into Ag plus, it is a cathode. This is what we have studied in galvanic cell. Now the first one is, what is the first question? The negatively charged electrode. So zinc electrode is negatively charged. I hope you remember. The second one is the current carriers in the cell. Okay, two things you have to mention. Electrons carry current outside the cell through wire. I remember electron. Children, you remember electron carries current outside the cell through wire. Whereas ions like Ag plus NO32 minus, I am talking about the salt bridge. So the ions which is available in the salt bridge is also considered to be a carriers of the current. Okay. So you have to mention both. The third one, current carriers in the cell. Okay. The third one, at each electrode the individual reaction you have to mention. What is that? Zn to give Zn2 plus electron released. Okay. This reaction will carry over an anode. Next one is on cathode. At the cathode, Ag plus will be gaining those electron converted into Ag. The next one is, how would you determine the standard electrode potential of the system? Mg2 plus into Mg. So now it is a very simple reaction. You will be writing the complete reaction. Platinum H2 in gaseous form converted into H plus, and salt bridge Mg2 plus converted into Mg. Okay. Now we know that electrode potential is equivalent to electrode reduction potential. Okay. So in using formula, E cell is equal to E cell of right minus E of left. Now what is that? Right hand side we know that Mg2 plus is converted into Mg, whereas left hand side H plus will be converted into H. Now we know that the standard potential value of hydrogen will be 0. So now E cell is equal to electrode potential of magnesium. That's all. Now the next heading is NERNST equation. So what is that? The NERNST equation provides a relation between the cell potential of an electrochemical cell, the standard cell potential, temperature and the reaction quotient. Okay. Now even under non-standard condition, I hope you remember, for the standard condition we will be using Xii, that is standard hydrogen electrode. Here we are going to talk about non-standard condition. The cell potential of electrochemical cell can be determined with the help of NERNST equation. The NERNST equation is often used to calculate the cell potential of an electrochemical cell at any given temperature. So not under the standard condition, any given temperature, pressure and reactant concentration. So the equation was introduced by a German chemist NERNST. Now the NERNST equation relates the potential of a cell in its standard state. Please remember, potential of a cell in its standard state to that of a cell not in its standard state. Okay, here the second standard state mentioning the temperature have to be 298 Kelvin, so it is not compulsory. So, for example, zinc 2 plus gain electron to convert into Zn solid form, or otherwise when you balance this reaction, 2 molecule of Zn2 plus will be combining with 4 electron to give Zn. So, now we know that from Le Chatelier principle that increasing the concentration of Zn2 plus, okay, in a electrolytic solution should derive the reaction to the right hand side. Okay, when you talk about right hand side, we are mentioning the product. In other words, it should decrease the potential of the half cell. Okay. Now, what will happen? The NERNST, for this condition, the NERNST equation allows us to calculate this increase for the above half reaction. What is the formula we will be using? E is equal to E naught under the standard condition minus RT by 2F Faraday ln concentration of Zn. A instead of A we can use concentration. So, concentration of Zn in solid form divided by concentration of Zn in 2 plus form, or otherwise for the second reaction E is equal to E naught minus RT by 4F on concentration of A or concentration of Zn whole square divided by concentration of Zn plus. Here I hope the terminology whatever we are having, it is very convenient one or comfortable one. E cell is equal to cell potential of the cell, E naught equal to cell potential under standard condition, R is equal to universal gas constant, T is temperature, N is equal to number of electron transferred in the redox reaction, F is equal to Faraday constant, Q is equal to reaction quotient. Suppose when you are using the common terminology, that is B molecules of B reacting with N molecule of electron to give and return back C molecule of C. Instead of using zinc ion reacting with the electron, directly we will be using. So, for this particular reaction, we can write the common NERNST equation as E is equal to E naught minus RT upon NF ln concentration of C power C divided by concentration of B power B. So, at 25 degrees Celsius, this equation can be simplified into E is equal to E naught minus 0.5916 volt upon N log of concentration of C upon C divided by concentration of B upon B. This therefore, as per the NERNST equation, the overall potential of an electrochemical cell is dependent on the reaction quotient. Okay, let me discuss about this in the next session.